So welcome to the New York City Category Theory Seminar. This is Josh Sussan on non-semisimple Hermitian TQFTs. This is the third in a computation and TQFT talk. Anyways, and this is the second time you're speaking here.
Yes.
Okay, very nice. Anyways, thank you. Go.
Thank you for the invitation to speak here again. So this is joint with Nathan Gear, Aaron Lauda, and Bertrand Patron-Morand. So this is going to be a little different from the previous two talks. It's higher dimensional, and the prospective applications are into classical computation and automata, but maybe possibly to quantum computation.
Lauda was in Columbia, but now where is he?
He's at USC now. That's right. Okay, so maybe I'll begin with some general an overview before I get more precise. So this section will be a little vague, but some motivation for everything. So if Q is some complex number, which is a root of unity, so it's an Lth root of unity, then you have some algebraic object, quantum group, say small quantum group, which you could attach to any Lie algebra. SL2, of course, is the simplest Lie algebra, so it's good to focus on this. So if we have a root of unity, we have something called small quantum group UQSL2, and it turns out using this, this algebra, you can construct invariants of three manifolds. So construct invariants of three manifolds. This is the Witten-Reshetikhin-Tarayev invariant, WRT. So Witten constructed this physically using quantum field theory. Reshetikhin and Tarayev really used this machinery of quantum groups to construct this invariant mathematically. Once you have this invariant of three manifolds, and we'll discuss this later, and we saw in the previous talks about universal construction, you could try to construct then a TQFT. So it's a three-dimensional manifold, so we would hope to construct a 2 + 1 TQFT, and that's exactly what happens. So there's a 2 + 1 TQFT, let's say to a surface sigma. We could associate a vector space V of sigma. So this is a surface, and this is some vector space. Okay, so this is a 2 + 1 TQFT. Okay, and so in order for a TQFT to be physically relevant, or for a vector space to be physically relevant, you would like for this vector space, the finite dimensional vector space, to have some sort of extra structure, like a Hermitian structure. So for physical relevance, want Hermitian structure, Hermitian bilinear form on V of sigma, okay, in order to do quantum mechanics. And more than that, you would like this Hermitian form to be positive definite. I'm not going to speak about that today because it's not clear we have that in what I'm about to speak about, but we will speak about this Hermitian form. Okay, so
just for the clarity, could you say what a Hermitian form is as opposed to a bilinear form?
Oh, sure. Yeah. So so first of all, for if you have a bilinear form, it's Hermitian if, well, first of all, it's sesquilinear, which means that, so it's linear, you add in both parts, but my convention will be that you could pull a scalar out in the first part, you have to conjugate. And now so that's sesquilinear, it's antilinear in the first component, and Hermitian just means that you have, if you take the complex conjugate, then you just kind of flip. So it's not quite symmetric, it's symmetric with this conjugation. So that's Hermitian form. Okay. So you want, so you would like your vector space to be equipped with such a form, and ideally you would also want this form to be positive definite. That the inner product of any vector with itself is positive, which is how normal physics, how quantum mechanics goes, but it's not necessarily a mathematical requirement. Okay, so so how do we kind of import this Hermitian form onto these TQFTs? Well, first let me take a step back. So Reshetikhin and Tarayev, I really should have written down their names, but Witten, Reshetikhin, and Tarayev. So Reshetikhin and Tarayev. So this primary example of a quantum group could be generalized. So they said that the category of modules over UQSL2 And in the next section, I'll talk more specifically what this is. So this is some category, this is some monoidal category. This could be generalized to a modular category. So this is generalized. And this, once you have a modular category, then you construct this T2 plus 1 TQFT. Get a 2 plus 1 TQFT. So really the category theoretical structure allowing for three-dimensional TQFTs is the notion of a modular category, of which representations of a quantum group is a primary example. Okay, so then the question is, well, what extra structure do you need on your modular category, your modular tensor category, to get these Hermitian forms? And this was, I believe I'll do to Turayev, well, maybe not all do to Turayev, but it could be found in Turayev's book. So Turayev defined the notion of a Hermitian category. Which I'll discuss more a little later on. And once you have the notion of a Hermitian category or Hermitian modular category, then you could get Hermitian's form on V of sigma. He also defined the notion of a unitary category, which is Hermitian category with some extra properties, and then you could get positive definiteness. But I'm not going to discuss that again today. Okay.
And is the goal to skip the ZM and just go straight from the UQ of SL straight down to the TQFT? In other words, Z of M of 3 is a polynomial usually, or something like that.
Yeah. So it's a complex number technically, but yeah, you could think of it as a polynomial in Q, but Q is some fixed complex root of unity.
Right. And so, but if the Reshtiv and Turayev are skipping that step, or they're not doing that, they're just taking UQSL2 and looking at the category of modules.
Well, I would say in order to define this three-manifold invariant, which I won't really discuss today, the general procedure, so a three-manifold, this is an old theorem of Licorice, you could realize any closed three-manifold is doing surgery on some link in S3, and then you have the machinery of Jones polynomials and things like this, so you could assign link invariance to this link defining the three-manifold invariant, and some summing procedure gives you this Z. And the Jones polynomial is defined through UQSL2. So I mean, I would say that this is completely connected to this. I mean, I also would say this is some sort of kind of very complicated evaluation in the spirit of these.
Right, yeah. You have to close it up. Yeah.
That's right. Okay, right, so Turayev defined this notion of Hermitian categories, which leads to a Hermitian form. So this category, UQSL2 mod, it's a modular category, it's a fairly, the construction of this is actually fairly complicated. This is some algebra, you look at category of modules. This category is non-semisimple. Okay? So not everything breaks down to a direct sum of simples. You have some short exact sequences which don't split. And so what Reshtiv and Turayev do in this obtaining a modular tensor category is they do some sort of procedure on this category called semi-simplification or purification. So they take this very complicated category and they do some procedure on this category to make it semi-simple. So,
is there a categorical definition of simplicity? I understand semi-simplicity is like a colimit, finite colimits, or a bunch of sums. But how would you just say simplicity in terms of a category?
I think I would say that the endomorphisms are just a ground field.
Thank you. Yeah, that's it.
Right. Okay, so
the
Reshtiv,
endomorphisms of the unit element. I'm just talking straight from a monoidal category.
So I would say an object is simple if its endomorphism algebra is just the ground field. Yeah.
This projection down to the semi-simple thing, that's radical.
Yeah, it's a I
mean, that's extremely forgetful.
Yeah, that's right. That's exactly right. So you're losing a ton of information.
Yeah.
And that's kind of maybe one of the big themes of what's been happening the last few years. So you're I mean, this is a very powerful invariant, but you do lose a ton of information.
Yeah.
And so Rashid can try. So just to they semi-simplify, and you lose a lot of information. Possible loss of information.
Is it like a localization or something? Like what does that do?
Yeah, so one way to think about it is that you kill, it's a quotienting. You kill objects whose quantum dimension is 0. And so the question was, is there a way to kind of preserve these things that you kill? Because when your quantum dimension is 0, I'm getting very vague right now, you can't use all this Rashid-contrived machinery. And so it turns out that there is a way of dealing with this. And so this was a series of few works starting around 2010, 2011. Non-semisimple TQFTs. So just a brief history. So Gear, Patero-Morand, and Turayev, they first defined link invariants where you could actually use some projective objects. So they defined non-semisimple link invariants. Okay, so kind of non-semisimple versions of the Jones polynomial. Okay, so they developed the concept of modified trace and modified dimension, and so they were able to recover non-zero invariants of things that were classically, or Rashid-contrived would say would be 0. Okay, once you have non-trivial link invariants, then you could go through this whole kind of WRT machinery, and so then in the work of Costantino, Gear, and Patero-Morand, they defined non-semisimple three-manifold invariants.
Yeah. Since we're being vague, so what does a non-semisimple? What does a non-semisimple link invariant not have that's missing that a typical link invariant does have?
So let me rephrase. So the problem is that, for example, if you color your link by some projective object or something, then the quantum dimension will be 0. And then just by the formal Rashid-Turayev machinery, you'll get 0 for when you close up. When you take your link, you present it by kind of co-evaluation, braids, close, you'll get 0. And so if you put in an object whose quantum dimension is 0, just all Rashid-Turayev will give 0. So they found a way of kind of defining a new kind of trace where you get something which is non-zero.
Mm-hmm. So these things are more powerful than a link invariant because they can differentiate different things that are 0.
A priori it's not clear if it's going to be more powerful, but it does turn out that it does do things that the normal thing does not do. Yeah, the intuition is yes. Because we're recovering things that used to be 0, and so yes, this feels like it should be more powerful. Mm-hmm. I don't know if it's strictly more powerful, but it does do things that the normal Rashid-Turayev thing does not do. And I'll talk about that also in a second. Okay, once you have a three-manifold invariant, as we saw in the previous talks, then you could construct, using universal construction, you could hope to construct a TQFT, and this was done by Blanchet, Costantino, Gear, and Patero-Morand. So they defined non-semisimple 2+1 TQFT. And so I would say, just to kind of reiterate, the goal today is to put a Hermitian structure on these non-semisimple TQFTs.
Huh. Can I just say that's beautiful. You now motivated your speech.
Okay, thanks.
Thanks. You should teach people how to do that. That's beautiful.
Thanks. Well, it's easy when the math is there for them. But
thank you.
So the goal is to put a Hermitian structure on this, And Turayev kind of gave the recipe in his book about how to do this in the semisimple case, and so we're going to mimic his arguments. And I should also really say that Kirillov and Wenzel also really contributed to, maybe in some examples, to the notion of Hermitian TQFTs, but really formalized very generally by Turayev. Okay, and so maybe just quickly, just to kind of speak to Nosan and people's intuition that this is more powerful. And so there are advantages to non-semisimple TQFTs. The first one is kind of general, but there's more flexibility. There's more objects that are now available to us, which weren't available because we couldn't deal with quantum dimension being 0. And there's also some extra technical data. You have to, in defining these three-manifold invariants, there's a cohomology class that's inputted. So there's more general structure, so there's more TQFTs now. Okay, that's kind of big. Oh yeah, so more concrete, at a fourth root of unity, these three-manifold invariants, so I should say that these are often referred to as CGP invariants. So CGP invariants at this particular root of unity, which is a fairly low root of unity, which is usually not very helpful in quantum topology, but even at this low root of unity, CGP invariants distinguish lens spaces.
It's low because the polynomials you get out won't be over degree 4. You won't get so many polynomials.
You're asking why is it distinguished, or
no? You said why it's not powerful.
So maybe that's not a great statement to make. I'm thinking more in terms of quantum computation. So, and maybe at the very end I'll say something about this. This is notion of topological quantum computation, and these classical WRT TQFTs are sources of, or potential settings for topological quantum computing. But at this lower root of unity, it's been known by work of Friedman and others that fourth root of unity is, the categories are kind of trivial. You can't construct all quantum gates at this low fourth root of unity. And so from that perspective, it's not particularly useful. Maybe my general statement about math I should remove, but yeah.
Is there some number that takes the place of 4, and then you can do every quantum gate?
Yeah, so I mean, so for example, the primary example is this Fibonacci category, which is UQSL2 semi-simplified at like I said, you could think of it as a 10th root of unity and take some subcategory.
Okay.
Which is 10th root of unity, 5th root of unity, there's a whole...
So this is like, like this ridiculous thing of discovering that some hardware thing in the 486 is Turing complete, the dirty page thing. So if it's too low, right, you don't get it, they're just, but then you reach it, suddenly, bang, you get everything.
That's very possible. I'm
sorry,
way too ignorant
sorry.
about computers.
Sorry.
Yeah. So the distinguished, lens spaces is a class of three manifolds, and this invariant is a perfect invariant of them, which is not true of the normal WRT thing. So this is, a sign that they're powerful. Maybe a third direct application. So you could look at the mapping class group of the torus. Say the torus. So this is the group of homeomorphisms of the torus. And by general TQFT constructions, this acts on the state space of the torus. And this action is faithful. Which is not true in the classical setting. And so you could really, so this is a sign that you can hope to understand mapping class groups really by looking at their representations. This injects as a subalgebra of endomorphisms here. And so then, okay, this proves in particular that the mapping class group of the torus is a linear group, it's a matrix group, which is already known because that's just SL2Z. But at least it's a sign that TQFTs are giving this statement now. And maybe even more promising, in general, more generally, if you look at the mapping class group of a higher genus surface, there are elements in here, have elements which have infinite order when acting, on V of sigma G. So you have an element in the mapping class group. This is a V of sigma G is a representation of the mapping class group. These elements have infinite order when acting here. That's not true in the finite case. So in the finite case, in the classical case, when you have finite order, that precludes the representation from being faithful. Okay? So you really need elements to have infinite order, because they have infinite order here. And so there's really a hope that, even generally, that these representations of the mapping class group are faithful, which is something that people in geometric topology, geometric group theory these would be new results. Yeah.
So I'm just trying to understand, you're saying, so we have these modular categories, and they could be semi-simple or not.
Yeah,
right?
yeah, that's right.
But if you're not semi-simple, does that include the semi-simple ones? Are you saying it's like a bigger, or is it like a separate thing?
Okay, so there's also kind of there's different definitions and terminology. I think maybe classically you would say that modular categories by definition are semi-simple.
Oh.
And so what these guys do is they define something called a G relative modular semi-simple category. And a particular, so this is a generalization, and then if you take a particular example of this, it does capture the standard semi-simple ones. So this is these G relative semi-simple modular categories subsume this.
Okay, and then they came up with a process to make each one of those semi-simple. Then there's like some machinery that gives you TQFTs.
So I would say that so this category starts out non-semisimple, then there's a classical machine which produces semi-simple. Reshtikin and Turayev would say you get 3 manifold invariants and TQFTs from this. And so what Gear, Padamora, and Turayev do is they say, don't semi-simplify. Okay, we need to deal with some issues like quantum dimension 0. They have a way of dealing with this. This is part of the data now of a relative modular category, and they did show that this relative G modular category does give TQFTs.
Okay.
Is that, for example, when you do this with algebras, you have a ring that is not semi-simple, and you take a closure that is semi-simple. What would be an example?
That's a good question. I can't think on my feet about that, but I maybe we'll talk later.
Can you just take a non-semi-simple algebra like Z mod n, then n is p to the k, and then mod out and get Z mod p. So mod out by the ideal, by the maximal ideal.
I mean, I think
it's a example that doesn't capture all the complexity. This is a example of going from non-semi-simple to a semi-simple structure.
I mean, then there's a question of like, okay, but then what topologically would you hope to get? I mean, I can't think off the top of my feet, but yeah, I mean, I think maybe like in these lower dimensional things, you could think about lower dimensional TQFTs. But anyway, sorry, I can't answer this.
This is not modeling out a category by an ideal to get a semi-simple category. It's not.
I mean, that's what this is. That's what semi-simplification is. It's modding out by some ideal to get a semi-simple category. Yes, you're modding out by some categorical ideal.
The category of very special modules. You don't just take all modules. You take very special modules over U2 and O2.
No, you really, okay, you take all, like, I mean, I'll discuss this more in the next section, but you take like all finite dimensional modules, yeah, which include crazy ones that you would normally exclude. I mean, it's still finite dimensional, so it's not that crazy. But.
So the classical, now classical Jones polynomial, Hamfly, Kaufman, they're all automatically semi-simple?
So the Jones polynomial, I mean, which you could define for generic Q, you don't need this modular thing. But yeah, the classic WRT, the 3 manifold invariants, they really come from a semi-simple thing.
Right, and so they give semi-simple, so you didn't have to do this semi-simplification.
No, you do. So this category which is presented to you,
yeah, It's not semisimple.
It's not semisimple. You do semi-simplification, then this semi-simplified thing is a modular category.
Mm-hmm.
And once you have a modular category, you have WRT, et cetera, et cetera.
Mm-hmm.
This thing by definition is semi-simple.
Mm-hmm.
Without this, it's not semi-simple. Quotient, you get this. You get a semi-simple.
But then these do include the semi-simple ones also then, right?
So, yeah, so the notion of this G relative modular thing,
Yeah.
so there's a lot of data in this definition, and one particular example does recover the semi-simple thing.
Yeah, so then when you say advantages here, like what I don't understand is like, you have a faithful representation for V, but
Yeah.
couldn't that be semi-simple? So then
So-
like that wouldn't.
Okay, yeah, so you have this G relative modular category, which there's a lot of data, there's some sort of group floating around, there's some sort of subset X. Okay. And so there's one particular choice, if you take like, and again, I'm not defining this, but if you take like X is empty or something, then you get the normal semi-simple thing.
Yeah.
If you take X to not be empty, like the integers, then you get the non-semi-simple thing. And so I'm talking about the applications of this choice of data, giving all of this stuff.
Can I say what I think he's unhappy about?
Yeah.
So you have the category of commutative rings. It sits inside the category of all rings. Okay? And here you have the category of semisimple things sitting inside non-semisimple things. So I think he's not happy with that word non. It should be, not
Just
necessarily.
on 3, right? Like,
Right.
you're saying this thing is faithful for non-semi-simple ones.
Yeah.
Right.
So that would mean that it's true for all semi-simple ones,
No.
No.
because semi-simple ones are all non-semi-simple.
Okay, I think you're right. I think I am abusing this word semi-simple or not semi. I'm using non-semi-simple as kind of like just a catchphrase
Okay.
to mean coloring things by representations we wouldn't normally.
Okay, I'm sorry, it's just.
No, no. Yeah, so I don't mean, okay. Non-semi-simple wouldn't.
Yeah, it's more
technically.
complicated.
Yeah. It's a particular, you're coloring by objects which are really are non-semi-simple. And when you color things by the actual semi-simple part of the category, then you get the the trivial things.
Got it, thanks.
Yeah. Other questions?
That's the clearest thing. Yeah, that's very clear. Yeah.
Okay, thanks. Okay, so this was again some motivation. I probably have to edit the talk a little bit, but at least let me take some time to define this UQSL2 or a related algebra. So just so we have some concrete definitions. So I'm going to talk about this quantum group unrolled SL2, which is a funny thing and not commonly known even in the quantum group world. It's very closely related to small UQSL2. So what is it? So
it's an example of a non-semisimple algebra?
It's exactly. It's an example of a non-semisimple algebra.
As opposed to usual SL2 or UQSL2 for a large Q.
Yeah. So SL2, just the universal enveloping algebra of SL2 is semisimple.
Mm-hmm.
Well, sorry. Its category of representations is semisimple. UQSL2, or Q is a generic parameter, semisimple category. When Q is a root of unity, that's when you start to see the non-semisimplicity, and this is an example.
Mm-hmm.
Okay, so I'm going to fix a root of unity, and for some technical reason, I'm going to take an even root of unity. Okay. And so now we let U, Q, SL2, I'm going to put this superscript of H, and I'm going to also just set this to be UH. This is an algebra over C. Generated by...
Is this your construction?
No.
So who is this?
I don't know who... The unrolled SL2, it definitely started appearing in this paper of Gear, Pedro, Miranda, and Tarayev. I think it goes back, at least in maybe there's signals of it by Otsuki. Yeah, I should say that almost nothing in this is mine. I mean, putting this Hermitian structure on it is what I was part of, but all these other things. So it's a C algebra generated by E K. So these are K inverse. So these are things you would expect when you start seeing quantum groups. But then this unrolled part, you throw in an extra generator H. And you should think of H as the normal diagonal SL2 matrix, 1 minus 1. Okay, so it's kind of a mix of quantum things with some classical things. Okay, with relations, so some standard relations, K and E almost commute, K and F almost commute. You have this mixed relation, EF minus FE, K minus K inverse, over Q minus Q inverse. So this is what you would expect when you see a definition of UQSL2. But now there's this extra generator H. And you should think of H as kind of the logarithm of K, or K is the exponential of H. Not part of the formal definition, but that's how you should think of it. And so some more relations. So H and K commute. Then you have kind of normal SL2 relations. Bracket of H and E is 2E. Bracket of H and F is minus 2F. Okay, so you have kind of UQSL2 relations, you have SL2 type relations. And then it's kind of common to also mandate that E to the R is F to the R, which is equal to 0. Okay, when you work with quantum groups of roots of unity, this is a condition which is also often imposed. Okay, so this is unrolled SL2. This is a definition of the quantum group which is going to be giving rise to the categories used for topological invariance. Okay, so now some more definitions. So I'm going to be talking a bit about the representation theory of this algebra. So if M is a module over this algebra, then we let M sub lambda, so it's a weight space. So it's all elements in M such that HM, so H acts diagonally with eigenvalue lambda, and K acts diagonally with eigenvalue Q to the lambda. Now, I said that you should think of E as K as the exponential of H, and I don't put that in the relations, but we do kind of insist on this in the representations. So K is kind of acting by an exponential of H. Yeah?
When you say representation, you mean like in the first month of introduction to representations of groups, no quantum stuff. That's what you mean by a representation.
That's what I mean.
You don't mean some further structure gets presented.
No further structure. It's a module, but yeah.
Thank you.
But do you want to think of H as some kind of logarithm?
Yeah, that's exactly right. Yeah, so you either think of K as the exponential of H or H as a logarithm of K. And I think that's kind of what, in this term unrolled, I think you kind of want, K is an exponential, so it's kind of like a circle, and I think you're unrolling the circle to include like maybe an entire line. So I think this H is kind of an unrolling of K.
So, I mean, if you think of this as Lie algebras, or something like that, you think of the relationship between a Lie algebra and a Lie group as somehow logs and exponentials or something like that. Is that what we're getting at? Or you said H is the classical part?
You should think of H as kind of the classical part. I have to think this through, but I don't think that we should really think of like the whole thing as being I wouldn't think about the Lie group's Lie algebra as an analogy, except for maybe the H and the K, but anyway. Okay.
So there's a half algebra structure?
Yeah, there's a half algebra. Yeah, there's a half algebra. I did not write down this data.
But H is primitive? Or?
Yeah, H is primitive.
But K is not primitive. Well, it is primitive. It is what
I forget what the primitive, but delta H is H tensor 1 plus 1 tensor H, and delta K is K tensor K.
Yes. Okay.
Okay, and so then.
One second.
Okay.
So so U of H, the unrolled one, is a Hopf algebra. So the category of modules is a rigid. I assume nothing's commutative here, so it's a rigid monoidal category.
Yeah, that's right. Yeah, and in fact, I'll state a theorem like this in a moment. Yeah, I mean it's a little bit more than that, but yeah. Yeah, and so M is a what? Okay, so M is a weight module if it's a direct sum of its weight spaces. Okay, and so now we let C be the category of finite dimensional weight modules. There's an R matrix. And a ribbon element. Theta. And so to say basically what Nasim was alluding to, so now the theorem is that C is a ribbon category. So it's a monoidal category. You could tensor representations. You could take duals. There's a braiding. So V tensor W is isomorphic to W tensor V using this R matrix. And so yeah, so this is it's kind of as good as you could get. Okay, so to now just analyze some. Let's look at some very specific objects.
It fails for non-finite dimensional. I mean, the duality fails. The rigidity
fails for
if you took a subcategory of it.
Oh yeah.
You didn't look at all modules. You looked at
I think that I think the duality would fail. Yeah. Yeah. Okay, so some objects in this category, so we could get maybe a little even more concrete. Objects. Let's see. So there are objects V alpha. So this is an R-dimensional module of highest weight alpha, and then there's some weird normalization, alpha plus R minus 1. So alpha is some complex number. Okay. So for each alpha you have this R-dimensional module of V alpha. And oh yeah, so highest weight, so for example, the weight space is highest weight space is just the unique vector annihilated by, let's say, E or F.
But say usually R-dimensional module has highest weight relative to H. I guess it's R minus 1, R-dimensional.
Yeah, that's right.
But here you have any complex weight?
That's right. Here you have any complex variable, any complex numbers.
But how is that possible? Is that
I mean, so
that's a highest weight relative to E. Oh, because E is truncated. Yeah. E is truncated?
E is truncated, yeah. Yeah, E is truncated, yeah. So the quantum dimension of these guys is 1 plus q squared plus q to the 4th plus q to the 2r minus 2, which is 0. So the quantum dimensions of these V alphas are 0. So these are things that would get killed in the semi-simplification process. You have modules Sn. So these are n plus 1 dimensional modules of highest weight n. And n goes between 0 and r minus 2. These are irreducible modules. These are simple modules. And in the semi-simplification process, these are the simples which survived. These survive semi-simplification. And then we have,
As opposed to the VAlphas?
they get killed under semi-simplification. One way to describe semi-simplification is that you should be killing morphisms, but the effect is to kill all modules whose quantum dimension is 0. And so these modules will die. So you never, when you construct link invariant or when you construct manifold invariant, you would never color by these VAlphas. They disappear on the semi-simplification.
So you later are going to try to make a bilinear form, and you're not going to have to worry about the SNs. You're going to have to worry about the VAlphas.
Essentially, yeah. That's the new part of the structure, yeah. These SN, so it turns, so I'll say something more specific in a second. These VAlphas are, when alpha is generic, which I'll make precise in a second, these are irreducible and projective. Okay. These SNs are irreducible, they're not projective. These SNs have projective covers, PM. So this is projective cover of Sn. These two have quantum dimension 0, so these would get killed. You would never color anything by these classically.
I'm sorry, you just had to say it again. Sn is clearly irreducible because that's simplicity. And VAlpha is not irreducible?
The VAlphas are,
Yeah.
for generic alpha, these are irreducible.
So,
But they have quantum dimension 0.
Mhm.
When alpha is generic, these are simple and projective. But they have quantum dimension 0, so WRT would not look at these at all. They would kill them. And I'll say what generic is in 1 second. I'm going to give a classification of all the irreducibles in this category. Clean this up a little bit. And then there are these extra one-dimensional modules, CKR. These are one-dimensional simple modules. With highest weight, KR, where K is some integer. Okay, so theorem. This is again not my theorem. I think this is due to Costantino, Gear, and Pattern Moran. So theorem, the irreducibles, or the simple objects in C are, you have the VAlphas, where alpha is some complex number, but it's not an integer unless it's a multiple of R. So generically, VAlphas are some simple object. You have these SNs, tensor CKRs, where again n goes between 0 and r minus 2, and k is some integer. And that's it. Okay, so these are all the simples in the category. So maybe just to give some graphical perspective as an example, so let's take R to be 5. So at every point in the complex plane, we have a simple. So if we take, let's say, this point Z in the complex plane, kind of this generic point, we have the simple, which I would say is V sub some alpha is V Z minus 4, just in my notation. Okay. So generically, that's what happens. On the real line, things are a little more interesting. You have at 0, S0, you have S1, you have S2, then you have S3, then I believe you have V0, and then you start tensoring with these CKs. So then you have S0 tensor C5, and so forth and so on. So generically, you have, in between, you have these other V's. But then you have these kind of weird things at integers. Okay, so this is a graphical depiction of all the simples in this category. So there's just a ton of irreducible modules for this quantum group. Okay, questions? Okay, so that's this. So this is some details about this main algebraic object. And so now I want to give you a definition of what a Hermitian ribbon category is.
I'm sorry, just KR.
Yeah.
CKR, so that's complex numbers.
So this is CKR is
No.
by definition it's a one-dimensional module with some basis vector, let's say V, where HV is K is equal to KR G.
Okay, but the SNs by themselves are irreducible.
That's right. That's right.
So one of your CKRs is going to be the trivial group.
So if K is equal to 0,
Yeah.
we recover the SNs.
Okay.
And so you have the normal S's, and then we think of it as then you have all these translations of the S's. Then you have S0 tensor C5, S1 tensor C5, blah, blah, blah. Then you have further and further translations. But K equals 0, you recover the SNs. Okay, so Hermitian ribbon categories. Okay, so definition.
And so this is your stuff.
This is still I'm defining something so due to Turayev. Yeah, I'll say at the very end the theorem that I was part of. So let's let C be a strict monodal category. We could think of just this category. A conjugation on C is a map dagger, which goes from, so it takes the Helm space of any two objects, M and N, and it returns out, so it takes a morphism between M and N, and it returns a morphism from N to M, such that it's an involution. F double dagger is F. The dagger of the composition, it's contravariant, and it respects the monoidal structure.
Well, why don't you call it a dagger monoidal category?
Is that a notion that's commonly known?
Yeah.
Okay.
Okay, sorry.
Yeah. No. Then yeah, it's probably correct. Yeah. Okay. So so that's a conjugation on the category. And so now a Hermitian ribbon category. Hermitian ribbon category is a ribbon category with a conjugation. For example, this category. Well, we can think, well, okay, a ribbon category, so it's a monoidal category with some extra structure. And so how does this dagger interact with the other structures in a ribbon category? So the braiding, which I'll just denote by this, So the dagger of this is the inverse braid. The dagger of the ribbon element is the inverse guy. Dagger of co-evaluation is evaluation. And dagger of this evaluation is this co-evaluation. Things that the natural things you would want, how it would interact. Okay, so I'm just trying to. I think I need to skip quite a bit about putting a dagger structure on these categories, but so maybe I'll start to state a theorem.
You want to say how the dagger relates to the rigidity? Because it's different. You know.
What? Why?
Because if you have a map from from A to B, so F star goes from B star to A star.
I would say it really no stars. I mean, maybe it's very closely related to this.
No, because, so write down. F goes from A to B. Okay. Dagger of F goes from B to A.
Yeah, dagger of F goes. Yeah.
Okay. But yeah, if you think of A and B as modules, then F star goes from B star to A star.
Oh, F star. Yeah. Okay. Yeah.
So if you think of a hop algebra.
Yeah.
Okay, so now F dagger and F star are not the same.
Then yeah, they're not. Oh, okay. That's your question. Is how to.
Right.
Okay, I can't answer your question yet.
I mean, you could have both structures. I mean, you
Yeah,
do have both structures.
You have both structures, yeah. And yeah, in general, this category B and B star are just different. Yeah, so I can't think. Yeah, I don't think that there's any extra kind of conditions to relate F star and F dagger. But
Right. So let's think of ribbons, real live ribbons, low dimensional topology ribbons. So F star is the ribbon turned upside down in some sense, going up.
yeah.
Okay, so what's the F dagger? Did you twist the ribbon? Did you?
So the condition is that you're doing the inverse. I mean, the ribbon is an invertible morphism, and so you just do the inverse of the ribbon morphism. That's the definition of what a ribbon dagger is.
Mm-hmm.
Right, because a ribbon goes from, let's say, V to V, so ribbon goes from V to V, so the dagger also goes from V to V.
So maybe dagger sounds like reflection on the horizontal plane. Dagger is like a reflection on the horizontal plane.
Yeah.
Possibly with orientation reversal.
But then, yeah, so it's kind of like a reflection in the horizontal plane
and
reversing orientation. Yeah. Yeah, so maybe that goes, maybe that
Right.
helps.
And the star?
But star is just this dual, it's just this rotation by 100, it's just rotation by 190 degrees. But and I think having this dagger would be like having an unoriented version of a category. For every morphism, you have a morphism back. So like you have an anti-involution on the set of morphisms. A bit like not having orientations if you're trying to, if there is having arrows. It sort of means that you can, for every arrow, there is an opposite arrow in the opposite direction. So it's a little bit like having an unoriented version of the notional category. A little bit like that.
Okay, so just take any Hopf algebra, look at the finite dimensional modules on it, you get a rigid category, etc. Now, and so it's a rigid category, so you have the star, so you think of oriented. And now you're going to add in this extra thing, this dagger, and so how is that related? How is so you have some oriented things, and now you have this dagger, and it just ignores the orientation, or?
It's like every morphism can use morphism back, going back. I'd be more thinking
I mean, it's not trivial that this dagger exists on the random category, ribbon category.
Right. He's like saying, he says to take a graph, a directed graph. If you want to make it undirected, then have an arrow going back every single time, so you have symmetry.
Yeah, I mean that's the graphical way to think about that. But to really construct that map back in the other way is not obvious how to do that. Yeah, you have to work hard on these categories.
I think there's some overlap because in cobordisms, if you have a cobordism, you can also use a cobordism going back. But then it's almost the same as rotation.
Yeah.
Those kind of additional relations in integrated cobordisms. Well, I think if you're ignoring orientations, maybe with orientations, the composition of the dagger and star in cobordisms is something like orientation reversal.
That's exactly that's a good one. That's exactly right. I mean, I'll try to rush at the end, but when we you need to define a dagger structure on the cobordism category, and basically if you have a morphism, cobordism from some surface to a surface, what is the dagger of that cobordism? Well, you're changing the source and target, and the dagger of that manifold bounding them is the same manifold but with opposite orientation. Okay. Then there's some more delicate things because you might have tangles in there and you have to deal with that. But yeah, but I think that's a good way to think about it. Okay, so maybe I'll just very quickly, so we have this notion of a Hermitian ribbon category. So I would like to say a theorem saying that basically this category C is a Hermitian ribbon category. So can't quite say that, but inside of this category C, we look at a category of modules with only real weights. We have to exclude, so we're now focused on the real line, but even the real line is still very rich. Normally you just have these dots, but you have infinitely many objects on the real line. And so we look at this category, we look at this subcategory, and so maybe theorem, and this is joint with Gear, Lauda, and Padron-Morin. So the theorem is that this subcategory D is a Hermitian ribbon category. There's some technical things that I have to omit now, but that's essentially the punchline. Okay, so maybe now I'll just quickly skip ahead to the TQFT part.
Let me just ask. Here you start with SL2, right?
Mm-hmm.
What about the rest of the special linear groups?
The higher SLNs?
Does that automatically come out, or we're working at that level, or it's a special thing to SL2?
No, it's not special to SL2, it's just easier, it's more concrete to deal with, but these theorems do hold.
Okay, well that's very interesting.
For SLN.
Okay.
No,
Understood, thank you.
yeah.
Certainly interesting.
Okay, so in the last couple of minutes,
Josh, you can go on till 8:30, whatever. I mean, whatever. This is absolutely fascinating. But
okay.
But if my attention to
okay, I couldn't. I just okay.
Whatever you want.
Okay, so I'll give you a few more minutes. I did skip quite a bit of material here, but so there's some technical things which are maybe not completely accurate about this theorem, but okay. So let's talk about Hermitian TQFTs. Okay, so a lot of these things we saw in the previous two talks, although in dimensions lower. So let's let Cobb the category of cobordisms in 2+1 dimensions. Okay, so the objects. So the objects are essentially surfaces, but there's a lot more data involved. the objects are surfaces, when we say sigma tilde, because sigma tilde is really the data of a surface, compact surface, some mark points, and some other things which are, I guess, not so important for us to discuss right now. And so these...
this mark points is what you call defects?
It's exactly right,
Okay,
yeah.
okay.
Yeah. So this is a compact surface, compact oriented surface. And so these are marked points in the surface, and they're labeled by objects in, let's say, D.
But he only talked about one dimension, and you're talking about surfaces, 2 dimensions.
That's right. So zero-dimensional defects on
And,
2 dimensions.
2 dimension.
Yeah. So these are marked points. Yeah, marked points.
So this is new. This is...
labeled by objects in D.
Wait.
Well, this is...
Labeled by objects.
he just labeled them with names, and now you're...
Representations.
No, the objects are labeled by objects?
Marked
Points
points.
are labeled by objects.
Points are labeled by objects.
By objects, okay.
Yeah. So representations.
Okay.
D, okay, fine.
Yeah.
So, cobordism, so fine, perfect, okay,
Yeah.
good. Sorry.
Are these are so-called real differentiable C-infinity manifolds, your surfaces?
I mean, we're in.
Are you in that
Yeah.
category, or no?
Yeah. I mean, we're in dimension. Yeah. Well, we're in
2.
dimension 2 and 3.
And the usual definition of C-infinity
Yes.
for these objects?
Yeah.
Okay, got it.
Yeah.
Got it, thanks.
Okay. So those are the objects.
Wait.
And I'm omitting.
Sorry. No, pay no attention.
Okay.
Thanks.
So there's some more data which I'm omitting.
Okay.
The morphisms are. Cobordisms are 3-dimensional manifolds.
Right. Okay.
So a morphism M tilde going from sigma tilde minus to sigma, let's say sigma 1 tilde to sigma 2 tilde. So this is the data of, so a 3-manifold. So the boundary of this 3-manifold, it's sigma 1, maybe with the opposite orientation, union sigma 2. Cobordism from sigma 1 to sigma 2. T, this is a ribbon graph.
Oh, you're gonna have to tell us what that is.
Yeah, sure. So this is, and I'll draw a picture in 1 second. Ribbon graph, colored. By morphisms in this representation theoretic category. Along with some other data, which is not so important. And so to draw a picture, so maybe this would be sigma 1. And there's some marked points, let's say we have like V2, V3 with some marked points labeled by some representations. So this is sigma 1, sigma 2, maybe some genus 3 surface. And maybe we have one marked point, V5. So the defects are labeled by objects in our representation theoretic category. And then you have morphisms of representations. You have intertwiners. So maybe you have a map from V2 tensor V3 into V5. This is some morphism. Maybe I draw a coupon, standard Rushdie contrived kind of graphical calculus. This is some morphism from V2 tensor V3 into V5. So it's a morphism in this category D. And so, more complicated, but this is essentially what I mean by ribbon graph. Does that help?
Yeah, no.
Okay. Okay, yeah, so, okay, I didn't say, but this is obviously a three-manifold. Okay, so now proposition.
I have a question.
Yeah.
The ribbon graph, are those, when you say colored by morphisms in D, that means the ribbon graph are morphisms in D that are being represented in this manifold.
Yeah, that's right. So we're inside. So I would say, yeah. So inside of this three-dimensional manifold, we kind of have like one-dimensional defects, and these one-dimensional defects are labeled. I mean, the zero dimensionals are labeled by objects.
Yeah.
And
And
so
the one-dimensionals are the morphisms.
yeah, that's right. Yeah.
So you drew two of them coming together, and then it's another thing. So that's actually, I mean, I was going to say to Gershom, they actually are like defects from what little I understand, because away from them you have nothing topologically. If you go around in a circle, there's no holonomy. But then they are indeed, I think it's not crazy to call them defects. The last lecture I thought that just dots, right? What do I care?
That's fine. So whenever you have representations of a group and you have a morphism from the product of representations
Yes.
of one, you can draw such a diagram. So you can always build networks of defects from representations of a group or half algebra.
Yes. Yes, no, I was thinking though that, you know, one had the notion of defect in a crystal lattice, right?
Yeah,
And you could believe, you know, that this
Yeah.
is...
Yeah,
So
I
the
think
way-
most of the
that's all.
time, I'm just because my lack of physics knowledge prevents me from many comments, but I think there are deep connections between physics.
Yeah, but as I said,
Yeah.
the last time they were like dots, right? What are they, defects?
No,
Are you
but
crazy? They're dots.
better.
No, now they're not dots. Now I'm willing to believe.
No,
Sorry.
but before he never said anything about them. They were just dots with names, and now
But the word defect was used.
I agree.
Is it purely...
I think of them as Feynman diagrams.
Yes. Not crazy.
Morphisms in the category of modules is Feynman diagrams.
Wow.
Intertwiners.
Yeah.
This is not crazy. No, it's not crazy. They tried to do this in the 19th century to get atoms. Stuff
Okay.
like this.
J.
Sorry.
We're gonna lose
Sorry.
him.
Yeah.
Yeah.
We only have him for 20 more minutes. We should squeeze him and make him come back next week and look after it.
Okay, so now maybe a proposition is that this category Cobb is a Hermitian ribbon category. So the tensor product is disjoint unions. Braiding and things like this are basically trivial. But I do have to explain a little bit about what is the dagger of a morphism. So what is M tilde dagger? So remember, M tilde is the data of a three-manifold and some ribbon graph. M tilde dagger, what Michael was alluding to before, so the underlying three-manifold is the manifold but with the opposite orientation. And the kind of more subtle part is what do you do to the ribbon graph. And so remember, T is, you should think of really as T as it's a morphism in your category D. And all the work of this theorem tells us how to take the dagger of that. So we have the data of T, and then we have T dagger. So T dagger is basically daggering all of these morphisms in the category.
So it would be phi dagger. Yeah, that's a phi in the.
That's a phi. So then you would have go from V5 to V2, V3, phi dagger.
Down. Right. Right, down, but really you're killing directionality. Okay, good.
But yeah, but really the definition of this phi dagger is not obvious. I mean, it goes into this theorem, yeah. Along with some other things. Okay, good. So now we're getting very close to defining this Hermitian TQFT. Okay, so we have the topological category all set up. Okay, so now I'm going to let Z be this CGP three-manifold invariant that I discussed in the beginning. Obviously, I don't have time to define this. It's some sort of kind of WRT type thing, but with some modifications. And so now I want to define the state space associated to a surface, and we saw this in the last two talks. So first, it's this first we start with this infinite dimensional space of all cobordisms from the empty manifold into your surface sigma. This is some gigantic space, and then we mod out by the kernel of some bilinear form, which again we saw in the previous talks.
Which kernel? Which kernel? The isotropic spaces or the what?
I'm gonna say what the
yeah.
I'll say what this
I
form
didn't know.
is.
Okay, that's all.
Yeah. So where this thing is, this form takes in a cobordism from the surface to empty across. Okay, so you take a cobordism from the surface to empty, empty to the surface, and so you take M1, so the pairing of M1 and M2. Well, if I kind of concatenate, I'm confusing the order, but so M1, M2 goes from empty to sigma to empty. So it's a closed three manifold, so now we can apply this evaluation to the CGP invariant. Okay, so this is the higher dimensional analog of what we saw in the previous two talks.
Michael called it alpha.
Michael called it alpha.
You're calling it C.
I will get confused if I change my notation.
No, that's...
Yeah, well, Michael called it alpha, that's right. Right, so, so it turns out that V sigma is a finite dimensional vector space, and it's fully monoidal, although that takes a lot of work. I'm hiding some details under the rug. You have to do some slight modifications to really make it monoidal. I mean, the whole point of the previous two talks was that they had topological theories which were not quite monoidal. Okay? If you do this construction on the face of it, it's again not quite monoidal. You have to do some fixing around to make it fully monoidal. But that can be done. Okay, and so now maybe the main theorem. So we have this CGP, this evaluation. We have these state spaces. And so now the theorem is that these state spaces, along with this evaluation, is a Hermitian 2+1 dimensional TQFT. So I have to explain what this means. Okay, so what does that mean? That means that there is this means that there's a form, a Hermitian form, on these state spaces. Okay, so what is this Hermitian form? So what is this state space? It's spanned by three manifolds which go from the empty to the surface. So I have a manifold which goes from manifold M1 which goes from empty to sigma, manifold M2 which goes from empty to sigma. Okay, I would like to cook up a number from this, and I can't quite glue because it's just the source and target are messed up. But with this dagger structure, I can. So this is equal to Z of M1 dagger M2. Because the dagger exchanges the source and target. They glue properly, you get a closed three manifold, you can take the CGP invariant. Okay, so this is a bilinear pairing. You could prove that this is Hermitian. And then furthermore, you have these nice functoriality properties. So furthermore, if we have, let's say, a cobordism W, which goes from sigma to sigma prime, okay, then that gives, this gives a map between state spaces. And so we have that M, W, N. So this is some bilinear pairing in V of sigma prime. This is the same thing as doing W dagger and N on V of sigma. So these cobordisms act as Hermitian operators, the Hermitian adjoint. Okay, so really the key to all this was being able to define this dagger structure on this cobordism category. And to define this dagger structure on this cobordism category, we needed to figure out how to take the dagger of a morphism in this unrolled quantum group. So all the technical work went into this theorem that I had a few minutes ago. So that's almost it. So I just want to say a couple of things about future work and open-ended questions. So this is a place where you could potentially do quantum mechanics. You want a Hermitian state space. What's not obvious, and which is not true in general, is that these forms are positive definite. You could have negative definite. You could have some things killing themselves. So that's bad for quantum mechanics. So what we're trying to do is we're trying to find examples where you do have positive definiteness and see, okay, places where you don't, are there other, do they have connections to other areas of math and topologies? Okay, so maybe this is a good place to formally stop. Okay, thank you.
I think we pestered you a lot.
I'm sorry, what was T dagger again?
So T dagger, I was, yeah.
Oh yeah, okay, so T here, but so, okay, I get it. So basically the, so M is reversed essentially, and then all the T's are daggered.
That's right.
Got it.
That's right, yeah. So you reflect, and then in this thing, this morphism is V dagger, which has a complicated definition.
You might as well tell me now what positive definite is supposed to mean.
Oh, positive definite just means that the pairing of any vector with itself is bigger than 0.
Okay.
So this happens in almost all normal circumstances.
Okay.
But
you don't know that for sure in this case.
you don't. Yeah, I mean, in fact, I have examples,
Mm-hmm.
which I was looking at for topological quantum computing possibilities, and I have some written down. But if I could look in my notes, where it's not true.
Mm-hmm.
Where, for example, V paired with itself is 0, V paired with itself is something negative. So that's probably a no-go for quantum computing, but I don't know, maybe it's interesting mathematically.
Well, wait, so you have this machinery, you start from this special little algebra, this quantum group, right? And then, okay, as you tell me, it works for a whole class of quantum groups of different dimensions. Okay, fine, that's great, okay. And then you get to cobordisms between surfaces, two-dimensional real manifolds. Okay. So, now obviously, if you go up to 3 dimensions, cobordisms between 3 manifolds, it's obviously completely different, right?
Yeah, that's kind of the subject of categorification and other areas of math.
Because what? You get terrible, in effect, coherence requirements, right? That are hard to even write down, right?
That's
Is that something like that?
That's definitely, as you go up in high dimension, things become, in this sense, more complicated.
Right, okay. So, now let me, this is really naive. So can you write down the Churlson constraints? Just write them down. Can you? For these kind of things.
What constraints?
The Churlson, who just died a couple of years ago, the guy who did the quantum Bell inequalities. So, you know, the Bell inequalities are purely classical, and they deal with classical field theories. And then
Churlson bounds.
Churlson bounds. There are similar things where you draw the Bell diagram, and then you say, now we allow the lines to transmit qubits or whatever ridiculous object mathematicians call it. And then Churlson showed there are similar bounds. You can't get everything. The no signaling polyhedron's larger than what quantum mechanics can give you. So maybe you can just write down, because you have enough stuff. You have these drawings, right? You have drawings. And the drawings are just like matrices. I mean, then there are rules of matrices at certain special points, right? So that's at the level of the Churlson, the Bell and Churlson bounds. That's just at that level.
Anyways,
Right? It's naive. But Churlson's, Bell's and Churlson's rules are huge. And they're topological. You show that they're topological. You're a professor. I'm sorry. I'm sorry.
So I don't know about
sorry.
that, but maybe just to say something about quantum computing, which I said in the very beginning, this will be a very, this will be very quick.
Touches on Samson and
So I don't know how many of you are familiar with like topological quantum computing. So going back to the semi-simplified thing, just to give a flavor of what is happening. So of course in quantum computing you want your finite dimensional Hilbert spaces, and you want your gates to be SU2 or SUN. And so there's this Fibonacci category, which I said before, you could construct it from semi-simplified quantum groups at 10 to the roots of unity, and then you take some subcategory. So this Fibonacci category has two objects, semi-simple, one in tau, so this is the monoidal unit, and you have tau. And it's called Fibonacci category because tau tensor tau is 1 plus tau. So you have this Fibonacci category, and you could construct a qubit from this category. So if you look at the space in, let's say, the Fibonacci category, this Hom space from tau, tensor tau, into tau, this is two-dimensional. And it's typical in this graphical language to draw these trees to denote these morphisms. So going from tau tensor tau down to tau. And there's two guys. And so tau tensor tau, maybe in language of physics, it fuses to either 1 or tau. So you could either have a monoidal object here, or you have the other object tau. And this is exactly this is a basis. So you can call this basis factor 0, and this basis factor 1. So this is a qubit, it's two-dimensional. And the whole idea of Friedman and Kataev about constructing topological quantum computers is that, well, this Fibonacci category, it's a braided category, so I could braid on the top. And so if I braid on the top, you get an endomorphism of the space. So I can either braid these first two or these second two. Okay, so you could get these braiding operators, and so if you braid the first two, we call it sigma 1. If you braid the second two, you call it sigma 2. And you could calculate that in this basis, you write down the formulas for R matrices. Sigma 1 is this diagonal matrix, e to the minus 4 q cubed. And sigma 2 is some other matrix. Phi is the golden ratio. Maybe these numbers aren't even very important to write down now. And one could show that the group generated by these two things, these two guys, it's dense in SU2. And you could approximate any quantum gate on a single qubit by these two things. And that's the whole idea of topological quantum computing. And so when we started out this non-semisimple stuff, we wanted to see, well, okay, if this is a semisimple category, what happens if you have non-semisimplicity? And one problem that we run into right away is this issue of non-positive definiteness. Depending upon what representations you have here, 0 paired with 0 might not be 1, might be 0. So that could be an obstruction to doing some sort of actual quantum computing. Okay, sorry, so that was a epilogue.
Something I thought I would mention, if you're not aware of, that like there's a lot in here that's not sort of like my jam or whatever, right? I could only follow so much, but do you know Paul-André Mellé's work?
Who?
Paul-André Mellé. He's a French computer scientist, does a lot of wild stuff. He had developed something that in 2018, I can give you the reference, called ribbon tensorial logic, since you were talking about all these ribbon categories. Mm-hmm. And it's a variant of tensorial logic that takes semantics in ribbon categories, and where every proof in this logic that's got sort of very fine-grained notion of negation takes semantics as a tangle.
Good.
Which is a proofs as tangles theorem. And so if you're talking about computation in this setting, I think that would be really interesting. I don't know, when you say Hermitian, I don't know how that would, that might be an axiom that could be expressed internally to ribbon tensorial logic, which would be really cool. I've no idea.
This is still classical computation, right? This is this formalism that you're...
It's a logic. It doesn't fit into classical, non-classical, and it's related to. He does a lot of work in linear logics, which are considered good settings for quantum computation. So I don't think calling it classical or not makes sense in this notion of computation. It's just.
But it's some linear. It's some you have vector spaces and.
They call it linear, but why is linear logic called linear?
Linear logic is linear because every element that gets introduced gets discharged precisely once, unlike normal, what we would call classical logic. But again, these words classical and whatever mean something totally different in the world of logic. That's, and what linear logic is used as a good setting for quantum computation because it models a lot of what happens with quantum computation. Because if once you read something, you can't read that qubit again because you've destroyed that information by using it. So that's sort of a linear notion. And so there's other people, that's a whole different story, that when they do quantum computation, the name of one of these fellows. Sorry, I don't want to go aside, but there's a whole other group of people that have written quantum programming systems using linear.
I mean, I don't know if this is related to Bob Koch's work. I don't know if that's a name.
No, it is. But the reason I'm highlighting Paul Andre's stuff is it doesn't relate to classical or traditional notions of quantum computation, but it's rather trying to develop a logic that naturally lives in the semantics of a ribbon category. And since that's really what you're building. That sounds like there's going to be something naturally of interest because it's naturally going to associate a new syntax to these ribbon categories and a new interpretation. Sort of, just by construction, right? Who knows what the physical version is?
I mean, so say if you say the name again, or if you.
I'll send you the link.
Thanks.
I mean, it's a linear category because think of a category with a product. So that has an and conjunction. Okay, so what you have A and A is equal to A, but now generalize from a product to a monoidal product, and there you don't have the universal property of A and A is equal to A.
Oh, okay. Okay.
I think we pestered him enough. Can we thank the speaker again?
I got a little more Fibonacci.